Hello, everyone, and welcome to the Basics of Compound Interest Part 2. So there's going to be three parts to the basics of compound interest. And then after that, we'll just dive into annuities. So what I want to talk about now is the realistic situation of, you make an initial deposit into an account, and then you make afterwards multiple deposits or multiple withdrawals. Okay. And there's really two ways to handle this very practical situation. There's the rather inefficient method of finding the balance after every transaction. And my experience is that quite a few people in this course actually do this method even, towards the end of the semester. They stick to this method. In real life, it's a very inefficient and not very useful method because, for example, if you're a landlord and you take in rent every month and you deposit into an account, 20 years, after 20 years, that's going to be 250 deposits. Do you really, if you're doing calculations involving that, do you really want to do 250 and do you want to really find the balance after every single month, 240 times? I think I said 250. I don't know why I said that, but anyway. And the answer is probably not. Okay. The other method is to accumulate each transaction and sum. And what do I mean by that? Well, particularly here, I mean withdrawals count as negative money. So both deposits and withdrawals, in this sense, accrue interest. Okay, and it makes sense to treat negative money as accruing interest because, or rather, it makes sense to think of withdrawals as accruing interest. The negative money that was withdrawn, or the negative money the withdrawal that counts as negative money accrues interest. And the reason why is that if you did not withdraw that money, then the extra money that you that would have been in your account obviously will accrue interest. So any money that you withdraw, you really have to think, hey, wait a minute, if I withdraw that's money that could have been accruing interest. That's a very important general principle and very important way of thinking in just general, if you open up a business or in any financial situation, that when you withdraw money, really that is money that could be accruing interest. All right. And in B, often time diagrams are useful. And I'm going to stress time diagrams throughout this course. They are just incredibly useful. And a time diagram is really just a diagram that illustrates when each transaction is made and how it accumulates interest. That's really all a time diagram is. So let's just dive into an example. I have an account that earns 7% effective annual interest, $1,000 initial deposit. Let's say $500 is withdrawn 6 months after my initial deposit. 1 year after my initial deposit, I deposit 250 more. And 2 years after my initial deposit, I withdraw $100. And finally, 3 years after my initial deposit, $200 is deposited. Find the balance after 3 years using both methods. And I'm just going to do I'm just going to do really both of these methods, these two methods, to illustrate that you get the same answer. All right. Okay, so let's do this problem using both methods. As we'll see, the first method is going to be very cumbersome, as I mentioned. It's not very efficient, but I guess it's not the worst thing in the world if you're an economics student and really want to, really like this method. But if you're a actuary student, you're definitely not going to pass exam FM if you insist on thinking like this. So yeah, so this is method A, and the point of the idea here is just simply see how much is in the account after every transaction, every withdrawal, or every deposit. So the initial deposit, well, that is just $1,000. Right. I do want to emphasize, though, and maybe I didn't make this clear enough in previous courses, if I give you a lot more, a much larger number of deposits or withdrawals on a quiz or exam, I'm definitely not checking, your answer doing this method, because that's an absolute nightmare for me personally to check. I mean, I don't think this is a good method, and you're basically making it a nightmare for me to check it using this method. So, I mean, if you get the right answer, I'll give you credit, but if you don't have the right answer, I might be harsh because I'm not checking all these calculations. But anyway, so, right, let's see what happens after 6 months. Sorry about that. Okay, well, this 1,000 accrues 6 months of interest. So we have 7% annual interest. So 6 months corresponds to 1/2 of a year. So the 1,000 accrues 6 months of interest. That's 7% interest. So that becomes 1,000, 1.07 to the 1/2. And after 6 months, we withdraw 500. So plug this into your calculator. You're going to get 534 and roughly 41 cents. All right, so 6 months later, I should also mention that I'm doing this method because it is conceptually very simple, and I want to just emphasize that using both methods, you do get the same answer, as you should. So after 1 year, well, this amount, 534 and roughly 41 cents, this this is going to accrue 6 more months of interest between 6 months and a year. So again, it's times 1.07 to the 1/2. And then we deposit 250 to get 802 and roughly 80 cents, like 79598. Okay, so after 1 more year, well, this 802 and roughly 80 cents accrues 1 year of interest. So it's 1.07 to the 1. Well, writing 1.07 to the 1 is a bit silly. So, it doesn't do anything. So it's just times 1.07. And we withdraw $100 after 2 years. And so this is going to be 758 and roughly 97 cents. All right, and last but not least, sorry, that's 99, not 97. Let's fix that. Okay, so after one more year, again, $758.99 roughly accrues 1 year of interest. So multiply that by 1.07. Oops. And we deposit 200 at the very end. So the amount we have at the end of 3 years is 112 and 12 cents. So I don't have to do any more calculations. So I'm going to round to the nearest cent. And it's kind of silly, but I just like to have dollar signs to emphasize, that this is an amount of money in the account. All right, so yeah, even with a relatively small amount of withdrawals or relatively small number of withdrawals and deposits, this is quite a pain in the ass. So, okay, so let's do method B. And remember, what's the idea behind method B? We're basically going to add up all the deposits and withdrawals, but before we do that, we're just going to see how much interest each withdrawal and each deposit accrues, and we're going to treat withdrawals as negative interest, so they accrue interest just like deposits would. All right, so let me draw a time diagram. You don't really have to draw time diagrams for every problem, kind of like this. I probably would not for this problem if I was taking a quiz or exam, but when in doubt, by all means, draw it. There's no harm. They don't waste that much time, and they can only really help you conceptually understand what the hell is going on. And that's a big part of this course when we're going to have kind of a lot of deposits and withdrawals, or have annuities, or just financial situations where there's a lot of moving parts. Just having a firm understanding of what's going on is really going to be the main challenge in getting the answer correctly. Okay, so let's draw a time diagram. So I'm just going to draw a timeline. Should make it a little higher so I can easily fit everything. Pretty good. All right, so yeah, so every 6 months I'll draw a little mark here. That's a pretty reasonable thing to do every 6 months. Okay, so we start off with 1,000. So what does that do? Well, at the end of 3 years, and give yourself plenty of room here when you draw a time diagram. So the 1,000 accrues 3 years of interest at 7% per year. So it's 1,000, 1.07 cubed. Okay, so we withdraw 500. Um, 6 months later. Didn't mean to do that. Sorry about that. Okay, so we treat that as negative. So this negative 500, this 500 withdrawal accrues 1.0. Accrues 2.5 years of interest, since we're making this withdrawal 6 months after our initial deposit, and we're trying to find how much we have at the end of 3 years. So 1.07 to the 2.5. At the end of the first year, we make a $250 deposit.
So it's getting a little cramped, but I should be okay. Make this a little higher, I suppose. And this earns 2 years of interest. 1 to 2, 2 to 3 is 3 years. We make a $100 withdrawal at the end of the second year. So that accrues 1 year of interest. And last but not least, we have our $200 deposit at the very end. Okay, so right, what I'm going to do basically is add all these up. Again, what's this method? This method is you add up all the deposits and withdrawals, except before you do that, you have to see how much interest each deposit and each withdrawal accrues. Okay. So, right, so, and maybe just to emphasize, I'll put a plus here, maybe make this red. Not that it really matters much, but so you take this number here, subtract this, add, subtract, add. You're going to get same answer, 1012.12.
So if you're really not convinced as to why withdrawals should accrue interest, let's just do a very, very simple example that should illustrate this. Let's just look at two scenarios, two very, very simple scenarios. Let's say scenario one, a person invests $5,000 at 8% effective annual interest and waits 6 years. And let's say a person essentially immediately makes a $1,000 withdrawal. So that's the effect of really only investing $4,000 at 8% and wait 6 years. But I'm kind of thinking, well, you initially invest $5,000 and immediately withdraw $1,000. Okay. Again, one perspective is that, you know, with that $1,000 that you've withdrew, that is money that would ordinarily sit in the account for 6 years and accrue interest. So let's just see exactly that at work. So in the first outcome, you have roughly $7,934.37. And then the second outcome, and of course, it's just 5,001.08 to the sixth, nothing very subtle there. And the second outcome is 4,000 times 1.08 to the sixth. That's 6,347.49. So the difference is most emphatically not $1,000. It's quite a bit more than $1,000. It's 1,586.87 cents. Okay. Right. So the point is that if you did not make that initial withdrawal of $1,000, you would have exactly $1,586.80 more than you would if you did make that initial withdrawal. So really, you know, to get the correct answer, you take, you know, the original investment without the withdrawal, and then subtract the withdrawal, accumulating 6 years of interest. And if you do exactly that, take outcome one minus this 1586.87, you're obviously going to get outcome two. I mean, all you're doing is 5,000 times 1.08 to the sixth minus 1,000 1.08 to the sixth gives you 4,000 1.08 to the sixth. Okay. So hopefully that makes sense. I mean, this is conceptually maybe a little bit tricky. I mean, in some sense, I think conceptually this concept is maybe one of the trickier parts of the course, kind of why withdrawals should accrue interest when you count it as, negative money. But anyway, hopefully this makes sense. Okay, so let me do another example, and we'll do examples like this throughout the course. So we have an initial deposit of 200, an interest account rate of 8%, effective annual interest. So you have only one deposit, and that's at the end of the second year. You make, withdrawals of $100 after 6 months and 18 months, and there's a withdrawal penalty of 2% of each withdrawal amount. Find the amount in the fund after 2 years. Okay, so for this problem, again, let's just draw a time diagram, and I'm just going to do method B. I'm not going to bother. I don't like method A, so I'm not going to continue on doing it. Yeah, let's draw a time diagram, and let's, and these time diagrams don't have to be works of art. Certainly, I'm not going to make works of art with a digital pen and pad, so, right. So let's draw markers at the end of each 6-month period. It's a little longer, but that matters much. Okay, so really this is the same kind of idea here. So we have my initial deposit is 200. I'll go a little quicker here. Right, so that accrues 2 years of interest at 8% per year, so 1.08 squared. Okay, so the quickest thing to do for this withdrawal is, let's just do the withdrawal and the penalty all at once. So you withdraw $100, but you have a 2% penalty on each withdrawal. So, well, what's 2% of 100? Well, obviously it's 100 times 0.02, which is 2. So it's really minus 102 here that you're essentially withdrawing. And I didn't do this, but it doesn't hurt to just draw dots, just to kind of emphasize that. I mean, it's not really necessary, but I guess it looks a little clearer. This is at t equals 0. This is the initial time. This is after 6 months, et cetera, et cetera. Okay, so right, this is minus 102, and again, it's practically speaking, you're withdrawing. In some sense, you're withdrawing $102, or $102 maybe more precisely is leaving the account one way or another, because you're withdrawing 100 and you have a 2% penalty on that 100. So that accrues, that total amount leaving the account, 102 minus 102. Well, 102 is leaving. That accrues 1.5 years of interest. So 1.08 to the 1.5. Yeah, and the same thing at the end of 1.5 years. So it's $100. Maybe move this over a bit. So it's minus 102. And again, there's a 2% penalty. And so that becomes minus 102, and that earns 6 months of interest. So sometimes I'll write 0.5 or raised to the 1/2. Hopefully it just doesn't cause any concerns. I mean, fractions versus decimals. Anyway, last but not least, at the very end, you deposit 150. So again, I'm going to add everything up. Oops, sorry about that.
Okay, so I'm going to add everything up. And that's going to be how much I have at the end of the 2 years. Right. So the answer is going to be 162 and roughly 80 cents.
All right, so let me talk very briefly about simple interest. So the idea of simple interest is that, so if we're dealing with a fraction of a year, or particularly if we're dealing with financial transactions that occur at microseconds, it doesn't really make sense to use compound interest, and compound interest is just too complicated to really do all these little tiny transactions at tiny little milliseconds or whatever fraction of a tiny fraction of a year we're doing with. So we need a kind of concept of interest that's no pun intended, a little simpler, and that is not subtly called simple interest. And that's exactly why it's called simple interest. It's just simpler than compound interest, and hence it's more effective when dealing with fractions of a year, particularly small fractions of a year. Whereas this is very, very, very unrealistic when for any time longer than a fraction of a year. So the idea of simple interest is, again, no pun intended, very simple. We say an account earns simple interest at interest rate I as a decimal if the accumulation function is just your initial deposit times 1 plus IT, where T is in years. Okay, so as a very simple example, this is basically just plug and chug. There's not a whole lot to this. Let's say you take out a 90-day loan of $50. It's made at 15% simple annual interest by the amount due after 90 days. Okay, so all we're looking at is we're trying to see what this $500 accrues to using simple interest after 90 days. And just like before, T is in years, so we got to convert 90 days as a fraction to a fraction of a year.
Okay, so this problem, yeah, it's pretty simple, no pun intended. So it's just plug and chug, really. So using the convention that there's 365 days in the year, after 90 days, how much does 500 accrue to? Well, it's just 500 plug and chug. 1 plus, it's 15% simple interest. So T here is, well, 90 over 365. That's what 90 days is in years. And just plug this into your calculator. Get 5, 18, and 49 cents.
All right, so let me do a much more interesting problem and something much more akin to something I would give on a quiz or exam. And maybe you would see something like this on Exam FM. Not sure if you would actually, but it's still, at least at the level of challenging. It's like at the challenge level of the Exam FM. Okay. And sorry, I should also mention that unless otherwise stated, we're going to assume compound interest. Compound interest is used much more often than simple interest. And like I said, simple interest is particularly used for small fractions of a year. So unless otherwise stated, we're using compound interest. Okay, so the last example I want to do in this video is as follows. A person invests $1,000 and withdraws all the money from this account once the investment fund or whatever hits $3,000. Effective annual interest is 7%. And for full years that the money is in the account, interest is compounded annually, so it's particularly compound interest, but for fractions of years that the money is in the account, simple interest is used. Okay. So the idea here is that, money sits in this account for a certain number of full years, and it accrues compound interest for all those years, and then it sits in the account for some fraction of a year, and for that fraction of a year, the amount earned in the account earns simple interest. Okay. When exactly does a person withdraw all the money? Okay. So we're going to employ, I don't know if I would call it a trick, but the idea of this problem we're going to use every now and then throughout this course. So it's a good problem for only that reason.
Okay, so the way we're going to do this problem is we're going to first find the number of full years that money sits in the account. And then after that, we're going to find the fraction of years that money sits in the account. Okay, and I should mention that, this is a idea. Again, I think I mentioned this, but this is an idea that is definitely used in future problems, and particularly it's an idea that is used in exam FM problems. So it's a definitely good problem to understand, and it's pretty straightforward. Okay, so how do we find exactly that? The number of full years that money sits in the account for? Well, we just basically pretend that throughout this duration that money sits in the account, we have compound interest. Okay, so we have 1,000 initial deposit. We have 7% yearly interest. It accrues to 3,000. So again, we're just pretending that throughout the whole time we have compound interest at 7%. Now we're going to solve for t. This is pretty straightforward. Just divide by 1,000. Take the ln of both sides. T ln of 1.07 is ln of 3. Right. So what you get? T is ln of 3 over ln of 1.07, and that's going to be equal to 16.24. Now what this tells me is the following. So we have 16 full years of compound interest. That's what doing this calculation tells us. And if you don't believe me, well, let's just see what happens if we have money sitting in the account for longer than 16 full years. Compound interest. So in particular, well, let's see what happens if we let it sit, this $1,000 for 17 years. Certainly if we let it sit for more than 17 full years, we'll just get more money. And let's just see that, well, we're not, if we do have money in the account for more than 17 full years, or more than 16 full years, then we're going to have more than $3,000, and that's the problem. Is that once we hit 3,000, we we withdraw all the money. So this is going to be, actually, if you dump this into a calculator, this is going to be 31588 . And okay, so the way we're going to do this problem is we're going to first find the number of full years that money sits in this account. So we're going to find the number of full years before withdrawal. And then we're going to find the number, the fraction of years that money sits in the account. Okay, so how do we do that? We're going to initially pretend that we are only dealing with 7% compound interest. So 1,000 is our initial amount. This money sits in the account until we hit 3,000. Again, we're pretending initially that we just have compound interest at 7%, and we're going to solve for what t gives us, and I'll explain what that tells us in a moment. So we take, well, we divide by 1,000. So if you're dying to know what t gives us, well, we're going to get t round down, and that's going to give us the number of full years before withdrawal. And then we're going to find the number of the fraction of years before withdrawal. Or rather, the fraction of years that money sits in the account after before we withdraw. Okay, so now just take ln of both sides, drop the t. T is going to be ln of 3 over ln of 1.07. That's going to be 16.24. So what does this tell us? This tells us that we have 16 full years So we have 16 full years of compound interest at an interest rate of 7%. Okay, why? Why is that if you're not convinced? Well, let's just check. Let's just see what happens if we let money sit in the account for 17 full years. Certainly, if we let it sit for more than 17 full years, we'll have more than if we let it sit for 17 full years. So let's see that if we let it sit for 17 full years, we're going to have more than $3,000. So in particular, if we let it sit for any longer than 17 full years, we're going to have we're going to have even more than $3,000. So not much to this, just, well, see how much we get. $1,000 sitting in this account, earning 7% interest for 17 years. Plug this into your calculator, you get quite a bit more than 3,000. It's actually 31.58 and roughly 82 cents. All right, so yeah, and this is just wrong. We said right at the money sits in the account for a certain number of full years, And then after that, it starts to earn simple interest. And then, this is basically what's happening until we hit $3,000. So money cannot have sit in the account for 17 or more full years because we withdraw once we hit 3,000. So we didn't do what the problem states. Okay, so what we need to do now is, now that we know how many full years we have of compound interest, we need to find the amount after 16 years, and this is pretty easy. We'll just do the same thing we did here, except 16. So it's 1,000, 1.07 to the 16, and that is, just dump into your calculator, it's going to be 2952. 16375. Okay. So let's say S, for lack of anything better to call it, is the time after 16 years that this amount of money sits in the account. Okay. So how do we solve for S? Well, it's not very hard. So 2952 and roughly 16 cents sits in the account for S years, where S is going to be a fraction, earning 7% simple interest. So this is a formula. It's 1 plus 0.07 times the amount of time this money sits in the account, this fraction of a year. Okay? And it sits in the account until we get $3,000. So you solve for S, and we get, just very straightforwardly, roughly S is 1/4. It's 0.23148. So the final answer is roughly 16 years and, 1/4 year. So it's roughly 16 years and 3 months. More precisely, it's 16.23148 years.